Water has quite a few unusual properties. One of them is famously called the anomalous expansion. So, we'll talk about what this is and what are its consequences. Alright, let's begin. Let's start with the meaning of this. Anomalous, what does that mean? Anomalous just means unusual. Unusual. So we're talking about unusual expansion in water. Let's take an example. Imagine we have some water, some amount of water, and let's draw some water molecules. And let's say the temperature right now is room temperature. Let's call that as 27 degrees Celsius. What we'll do now is we'll cool it down. Let's cool it. We'll cool it down. What's going to happen? Well, as you cool it, its temperature will drop. And as the temperature drops, the molecules of water start losing energy, because of which they vibrate slower and they end up coming closer to each other. And as a result, the whole water ends up shrinking. Now, we have spoken about this in a little bit more detail in some previous video. And so if you require more clarity, it would be a great idea to go watch that video and then come back over here. But anyways, water contracts on cooling. All right, so let's write that down. As temperature decreases, so we decrease the temperature, what we will see is water ends up shrinking. So water contracts or shrinks. Let's write that, shrinks. Now, there's nothing unusual about this. This is normal behavior. When you heat things, they expand, and when you cool them, they contract. So again, this is normal. This is normal. But this normal behavior only continues until you hit 4 degrees Celsius. Because once you go below 4 degrees Celsius, something very unusual happens. All right, so let's write that down. Until we hit 4 degrees Celsius, we will see water contracting like this. Water keeps contracting. So the water would shrink. Now, I've highly exaggerated over here for effects, but water shrinks. And this continues until 4 degrees Celsius. So until we have hit 4 degrees Celsius. Everything is normal so far. But you cool it down even further. Cool it further, and now you will see, mysteriously, water doesn't shrink anymore. Instead, it expands. And that is what we call as the anomalous expansion. Again, let's write that down. If you further decrease the temperature, we would expect the water to continue shrinking because that's normal behavior, but it doesn't. Instead, you will see it expanding. It expands. And this is very unusual. We don't expect this to happen, right? This is unusual. So let's write that down. Again, let's copy this. Copy and paste. We would expect the water to shrink further, but it doesn't. Instead, it expands. Again, I've exaggerated it for effects, but you get the idea. And you could cool all the way down to 0 degrees Celsius and you will see this anomalous or unusual behavior, but don't stop there. Cool it even further. Cool it even further. What happens next? Well, we have now reached the freezing point of water, so water will start crystallizing into ice. And you will see that even when it is crystallizing, even during this particular process, the unusual behavior continues. So even during crystallization, we will see a continued expansion taking place. So it still expands over here. Again, this is also unusual. You don't expect that to happen. All right, so our ice at 0 degrees Celsius, temperature doesn't change, remember? Only the phase changes at 0 degrees Celsius. But anyways, during this time, ice keeps expanding. So from 4 degrees Celsius to all the way 0 degrees Celsius ice, during this region, we are seeing an unusual expansion. And the unusual behavior is not just when you cool it, but even if you were to heat it up. If you had to heat up ice, it would melt. And even if you had to further heat up and increase the temperature from 0 to 4 degrees Celsius, you would see now, instead of expanding, it would contract. All right, so from 4 degrees Celsius to 0 degrees Celsius ice, in this phase, you will see unusual behavior. If you're cooling it, it'll expand. If you're heating it, it will contract. That's the idea behind this. Now, you may be curious to know what's the reason behind this anomalous behavior. Why does water act so weirdly between 4 to 0 degrees Celsius? And why only between this temperature? Well, we'll talk about the reasons behind this in another video, but as of now, let's look at the consequences of this. I mean, what's the big deal? So yeah, water expands when you cool it below 4 degrees Celsius, but what's the big deal? What happens because of that? Well, let's talk about that. Let's make a little bit of room. All right. The first consequence can be thought of this way. Now, imagine you have water now right at 4 degrees Celsius, and suppose you cool it down. Well, it expands. What if you had to heat it up? Well, it would still expand, normal behavior. So either ways, notice water expands. So if you look at the molecules of water, either ways, even if you cool it or you heat it from 4 degrees Celsius, they will go farther away from each other. That means the molecules are the closest at 4 degrees Celsius. Does that make sense? In other words, the molecules of water are most crowded at 4 degrees Celsius. In physics, we could say the density of the water is maximum at 4 degrees Celsius. Density is a measure of how crowded things are. Since water is the most crowded at 4 degrees Celsius, it will have maximum density at 4 degrees Celsius. So that's one consequence we can write. So consequences. So the first one is it has maximum density at 4 degrees Celsius. At 4 degrees Celsius. And that density is 1000 kilograms per meter cube. Which means if you were to take 1 meter cube of water at 4 degrees Celsius, it would weigh 1000 kilograms. At any other temperature, it will have lower density. So the density at any other temperature would be less than 1000 kilograms per meter cube. Now, this may not seem like a big deal, but think of it this way. The unusual behavior continues even when water is crystallizing into ice. Even when ice is being formed, molecules are going farther away and the density is decreasing. Because of this, ice has lower density than water. Let's write that down. Ice is less dense than water. And if you think about that, water is really special because most solids are denser than liquids. You may have already learned about that molecules are more tightly packed in solids, high density. But that's not the case with ice. Ice is less dense than water. And this is the reason why ice floats on water. We take this for granted because we see this every day, but if you think about this, that's really special. Ice floats on water because of this anomalous behavior. But there's another very big consequence because of this anomalous behavior. Let's make a little bit more space for that. All right. So the third consequence is that aquatic life, so let me just draw on fish over here. Aquatic life can survive in very cold conditions. Very cold conditions. And here's how that works. Now suppose this represents a lake or a pond in a very cold place. Let's say the surrounding temperature is below 0 degrees Celsius. We would expect this entire water to freeze up, right? Because the whole temperature is below 0 degrees Celsius. But it doesn't. And it's all because of this anomalous behavior of water. So what happens is that the top layer of the water, which is in direct contact with the surrounding, well, that will end up freezing. That will end up becoming ice. Now imagine there was no anomalous expansion in water. Then ice would be more dense than water. Ice would sink and the rest of the water would come on top, and again the process would continue and the whole water body would solidify just like we would predict. But because of the anomalous behavior, ice is less dense than water, which is why the top layer of the ice doesn't sink, but instead it floats, and it doesn't allow the bottom water to freeze up. It doesn't allow the bottom water to come in contact with the cold surrounding. It insulates the bottom water, and which is why the water below can stay warm. And this is why oceans and lakes at very cold places don't freeze up. Only the top layer freezes, and then it acts like an insulator and keeps the water below pretty warm, making our aquatic friends very happy.